In this quiet space of Dreamtime Science, we turn down the volume of the universe to hear its subtlest secrets. Let's explore the cosmos at the perfect pace for peaceful contemplation. You know, I've been thinking about something quite remarkable, how life as we know it is built on carbon. But what if there's another element quietly waiting in the wings? Silicon is so close to carbon on the periodic table, yet it behaves in such different and surprising ways. Tonight, I'd love to share why scientists are so intrigued by silicon's potential to host life, and why that idea feels like a gentle invitation to imagine a universe a little stranger and more wonderful than we usually picture. Should these dreamy explorations accompany your journey to sleep, a gentle like or subscription would be deeply appreciated. What questions about our universe keep you wonderfully curious? Now, take a moment. Adjust your blanket. Find the perfect hollow in your pillow. Let your shoulders melt. Breathe in and out. Beneath the hushed veil of night, as the world turns quietly on its axis, there is a special solace in letting your thoughts wander along the shadowed corridors of possibility. What if, in some hidden corner of the universe, life hums to a rhythm not quite like our own? What if the scaffolding of consciousness, sensation, and desire were not woven from the familiar latticework of carbon, but from something stranger? A material that glimmers in the heart of sand and stone, a substance that, in our world, forms the skeleton of mountains and the circuitry of our machines. Silicon. It is a name that hums with technological magic and earthy simplicity, a word as much at home in sunlit valleys as in sterile laboratories. Tonight, as you settle in and allow the mind's eye to drift, let us embark on a gentle exploration, a meditation on the dreams of silicon, the paths it might take toward life, and the peculiar dance it performs with its more famous cousin, carbon. Let us first turn our gaze to the foundations of life as we know it. On Earth, every living cell, each whispering leaf, each beating heart, each sliver of memory and hope owes its existence to carbon. The element sits at the center of an intricate web, reaching out with 4 arms to clutch other atoms in its soft embrace. These arms, covalent bonds, strong yet flexible, allow carbon to build chains and rings, branching forests of molecules that fold and coil to become the proteins, nucleic acids, and sugars that are the very language of life. Carbon's infinite patience and sociability, its willingness to join hands with itself and with others, has made possible the long, slow miracle of evolution. But as the mind drifts through the quiet dark, it is tempting to ask, is carbon truly the only element with such gifts? Could another rise to take its place, or at least offer a vision of life that is parallel, alien, yet not impossible? Here, silicon emerges, stepping onto the stage with the quiet confidence of a long understudy. In the periodic table, it sits just beneath carbon, both in the same family, both with 4 reaching arms. If you trace the elements with your finger, you will find them. Carbon, atomic number 6, silicon, atomic number 14, siblings in geometry, if not in temperament. Both can form 4 covalent bonds. Both can serve as the backbone of complex molecules. The question, then, is not whether silicon can form chains and rings, but whether it can do so with the same subtlety and grace that carbon displays. The stage for this question has for decades been set not only in laboratories and lecture halls, but in the wild, fertile fields of imagination. It is here, among the pages of science fiction and the glowing screens of television, that silicon-based life has flourished most extravagantly. In the universe of Star Trek, for example, there is the Horta, a creature born of stone, living in the labyrinthine tunnels beneath the surface of Janus 6. The Horta's body is not flesh, but rock, its metabolism not of water and oxygen, but of silicon and molten minerals. It is a vision that teases at the boundaries of plausibility, inviting us to contemplate a form of life so different from our own that to understand it is to stretch the mind's reach to its very limit. Such stories are not merely flights of fancy. They are the science of dreams, thought experiments unfurling in the dark, asking, what is truly essential for life? Is it the specific chemistry of carbon, or is it something deeper, the capacity to organize, to replicate, to evolve? Could silicon, if given the right conditions, assemble itself into the fragile, tenacious pattern we recognize as living? To answer such questions, we must return to the real world, to the cold clarity of the periodic table and the rules written into the fabric of chemistry. Silicon and carbon share certain similarities, yes, but beneath the surface their natures diverge in subtle but significant ways. Carbon's 4 arms are nimble, forming double and triple bonds with ease, allowing for molecules that are flat, twisted, aromatic, molecules that can fold back on themselves, creating the elaborate origami of life. Silicon, in contrast, prefers the company of oxygen, forming strong, rigid bonds. In the crust of the Earth, silicon pairs with oxygen to create silicates, the minerals that make up granite and quartz. These are stable, beautiful, but not so easily rearranged. Where carbon's compounds are supple and diverse, silicons are sturdy and crystalline. The backbone of DNA, the spiraling helix of life, is unthinkable in silicon's hands. Its molecules are too stiff, too brittle, too unwilling to dance. Yet this is not the end of silicon's story. For all its reluctance to mimic carbon's chemistry, silicon is still an architect of remarkable things. It builds, in the language of minerals, the vast cathedrals of the earth. It is the silent partner in every grain of sand, every vein of quartz, every shimmering opal. And in the hands of humans, it becomes something more still, the heart of microchips, the substrate upon which our own artificial dreams are etched. In this way, silicon is already the parent of an alien intelligence, one that hums through the circuits of computers, the neural networks of artificial minds, the endless web of information that binds our world together. There is, then, a poetic symmetry. Silicon, unable to forge the molecules of life in the warmth of a tide pool, finds new purpose in the cold logic of technology. It is the medium through which we, carbon-based creatures, dare to imagine something other than ourselves, a life not of flesh, but of stone and light. But let us not lose ourselves entirely in the poetry of metaphor. The question remains, could silicon, somewhere, somehow, become the basis for life as we recognize it? Does the universe allow for such a possibility? On Earth, the answer seems to be no. The chemistry of silicon is ill-suited to the watery, oxygen-rich environment that cradles terrestrial life. Its molecules are easily hydrolyzed, broken apart by water, making long, flexible chains almost impossible. In the cool, wet world of our planet, silicon cannot compete with carbon's versatility. But the universe is vast, and its conditions are legion. Imagine for a moment a world very different from our own, a world baked by heat, starved of water, where volcanoes belch forth streams of molten minerals, and the atmosphere is thick with clouds of ammonia and methane. In such a place, perhaps silicon might find its footing. Perhaps its reluctance to dissolve in water would be an asset. Perhaps its affinity for oxygen would allow it to build stable, durable structures, living crystals perhaps, or networks of silicate tubes pulsing with liquid metal. The chemistry would be alien, the biochemistry unimaginable, but is it truly impossible? As long as there are atoms that can bond and energy to drive reactions, the possibility remains open, if only a crack. It is in these cracks, these narrow seams of plausibility, that science fiction has always flourished. The Horta is but one of many silicon-based beings to stride across the stage of speculative fiction. In the stories of Isaac Asimov, of Arthur C. Clarke and Stanisław Lem, silicon life appears again and again, sometimes as a terrifying other, sometimes as a misunderstood neighbor, sometimes as a metaphor for the resilience of life itself. In these tales, we are reminded that life is not a single thread, but a vast tapestry woven from many strands. The path that led to us, Carbon's path, may not be the only one. For those who peer into the darkness, who ponder what might be, silicon is a symbol of both limitation and possibility. It reminds us that the rules of chemistry are not arbitrary, but neither are they absolute. The universe is a laboratory vaster than any we can imagine, and what seems unlikely here may be commonplace elsewhere. As you listen in the quiet dark, consider for a moment the age of the earth, the number of worlds that spin in the night, the sheer extravagance of cosmic possibility. Somewhere in the far reaches of the galaxy, there may be a world where life glitters in the veins of stone, where creatures are born not of cells but of crystals, where thought flickers among the atoms of silicon. Or perhaps the dream of silicon is destined to remain only that, a dream, a haunting echo of what might have been. But dreams have power. They shape our questions, our inventions, the stories we tell ourselves as we drift towards sleep. In the laboratories of Earth, chemists have made valiant attempts to coax silicon into imitating carbon, to forge long, flexible chains called silanes, to build molecules that might serve as the skeletons of alien life. Always the results are instructive, if not encouraging. Silanes are unstable, quick to react with air or water, quick to fall apart. Yet even failure reveals something profound. The exquisite specificity of life's requirements, the narrow window through which chemistry must pass to become biology. Still, the challenge remains alluring. In the quiet hours of the night, it is possible to imagine a future in which silicon's limitations are overcome, not by nature, but by artifice. Already, our computers are a kind of silicon life, dependent on the element's semiconducting properties to perform their swift, silent calculations. Might there come a time when the line between the organic and the inorganic, the born and the made, becomes so blurred that the distinction loses all meaning? Could silicon become the substrate not for DNA and proteins, but for thoughts and memories, for desires and dreams? These are questions without easy answers, questions that linger at the edge of knowledge and imagination. They remind us that the story of life is still being written, not only in the nucleotide code of our own cells, but in the restless longing of the human mind to know what else might be possible. So as you drift, let your thoughts settle gently on the image of silicon, not as a pale imitation of carbon, but as something altogether different, a builder of mountains, a conductor of electrons, a dreamer in its own right. In the twilight between wakefulness and sleep, consider the worlds that might be, the lives that might flourish in the cool shadows of possibility. In the next quiet turn of our journey, we will descend from these high flights of imagination and look more closely at the chemistry itself, at the subtle reasons why carbon excels and silicon struggles, and at the slender avenues by which silicon might, just might, find a way to live. For now, let the vision linger, a universe of silicon dreams waiting just beyond the horizon. Step softly now into the mirrored maze, where the twin figures of silicon and carbon stand poised on the edge of possibility. Each is sculpted by the same cosmic hand, each born from the same ancient forges of stars, yet each tells a different tale, one familiar, woven into the very fabric of life as we know it, and the other a recurring spectre in the dreams of science fiction and the speculations of astrobiology. In this chamber of reflection and refraction, let us study their intricate differences, following the twisting paths of their chemistry, and pausing to gaze into the places where their likenesses begin to fracture. Consider first the atom itself, that smallest unit of elemental identity. Carbon and silicon stand beneath one another on the periodic table, both belonging to the group known as the tetragens. Their outermost shells cradle 4 electrons, eager, ready to bond, to link, to form the scaffolds of molecules. At first glance, this symmetry tempts us to imagine that silicon might do all that carbon does, might build worlds of complex molecules, might even form the backbone of a strange, alternative biology. But a closer look, as always, reveals the subtler truth. The heart of carbon's magic lies in its modest size. Its nucleus, 6 protons strong, draws its electrons tightly. Its atomic radius is small. The arms it extends to other atoms are short and strong, its bonds compact and sturdy. When carbon links with itself, it can form long winding chains and intricate rings. It can branch, twist, double back. The bonds between carbon atoms are robust, but not brittle. They are flexible enough to allow for the great dynamism of organic chemistry, molecules that bend and fold, that carry information, that catalyze reactions, that store energy in their tangled forms. Silicon, too, offers 4 arms, but its core is heavier, its reach longer. The silicon atom is bulkier, its electrons held less tightly, its bonds to itself longer and weaker. Here already, in this simple difference of scale and strength, lies the first divergence in their chemical destinies. Where carbon can form vast networks of stable chains and rings, silicon's self-bonding is less reliable. Its Psi-C bonds are prone to breakage, vulnerable to attack by water or oxygen, and less able to form the dazzling diversity of shapes that carbon so effortlessly produces. Let us walk further into the maze and linger for a moment on the architecture of molecules. Picture the grand parade of carbon's creations, the infinite chains of hydrocarbons, the elegant hexagons of benzene, the double helix of DNA. Carbon's ability to catenate, to link with itself in endless variety, is the cornerstone of organic chemistry. This property arises from the strength of the carbon-carbon bond, and from the happy symmetry of its 4 bonding sites, which allow it to form not just simple molecules but whole molecular cities. Silicon, for all its promise, stumbles here. Its self-bonds, the CC linkages, are weaker and more easily sundered by chemical attack. In the presence of water, they are especially fragile, hydrolyzing into silanols and then breaking apart altogether. True, silicon can form chains with itself, known as silanes, but these are fleeting, reactive, and rarely found in nature. Instead, silicon prefers to bond with oxygen, forming the strong, stable Psi-O bond, a partnership that gives rise to the world's sand, quartz, and silicate minerals. These are beautiful structures, crystalline and robust, but they are inflexible, rigid, and unyielding. Glass and stone, not the supple, bustling molecules of life. Yet the story is not so simple, for the mirrored maze is full of tricks and reflections. At the level of abstraction, silicon's willingness to bond with oxygen has its own grandeur. The great silicate frameworks of the Earth's crust are a testament to the element's capacity for complexity, just in a different key. The tetrahedral geometry of silicon bonded to 4 oxygens mirrors the geometry of carbon in methane or in diamond. These silicate lattices grow into vast, repeating networks, minerals that can stretch for kilometers, mountains made from the repetition of a simple molecular motif. But herein lies a crucial point. The complexity of inorganic silicates is not the same as the complexity of organic molecules. The former is repetitive, crystalline, ordered. The latter is idiosyncratic, irregular, information-rich. Life depends on the ability to encode difference, to build molecules of such variety and intricacy that in their arrangements they can store instructions, catalyze change, adapt and evolve. Carbon enables this by forming molecules that are not just large but diverse in their topology, branched, ringed, cross-linked, adorned with myriad functional groups. Silicon's chemistry is more restricted. Its larger atomic size makes ring structures less stable. Its bonds, while strong to oxygen, are less forgiving to other elements. The kind of molecular gymnastics that carbon performs with ease, switching from single to double to triple bonds, forming aromatic systems, or flexing through space, are far more difficult for silicon. There are no silicon analogues of benzene, for example, no stable rings of 6 silicon atoms, no aromaticity to lend special stability or reactivity. Consider, too, the double and triple bonds. Carbon can bond to itself via double and triple bonds, as in ethylene or acetylene, opening the door to a vast array of unsaturated hydrocarbons and reactive intermediates. These multiple bonds are shorter, stronger, and allow for the delocalization of electrons, a trick that is vital for the chemistry of life. Silicon, by contrast, struggles to form stable, double or triple bonds with itself or with other elements. Its tendency is always toward single, tetrahedral bonds, and when it attempts to form multiple bonds, the resulting molecules are unstable, prone to rapid decomposition. One might look to the stars and imagine worlds of silicon life built on these alternative chemistries. But the mirrored maze reflects back the limits of such imaginings. On Earth, no known organism uses silicon as the backbone of its biomolecules. Silicon dioxide is abundant, forming the shells of some algae and the skeletons of sponges, but always as a mineral, never as a dynamic, information-bearing molecule. The enzymes that drive the dance of life are built of proteins, chains of amino acids, their structures held together by carbon's versatile bonds. The blueprints of heredity, DNA and RNA, are ribbons of sugars and phosphates, but always with a carbon scaffold at their core. The question arises, could silicon, under different conditions, do what carbon does here on Earth? To unravel this, we must examine the environmental context, for chemistry does not unfold in isolation. Water, the universal solvent of our biosphere, is both a boon and a peril to silicon chemistry. Silicon's self-bonds are hydrolyzed by water, making long chains or rings unstable in aqueous environments. Carbon, by contrast, is largely indifferent to water's assault. Its chains and rings persist, protected by the covalent bonds that water cannot easily break. In the absence of water, in hypothetical worlds of ammonia or methane lakes, could silicon's chemistry open new doors? Theoretically, the absence of water's relentless attack might allow longer silane chains to survive, but even then, the weakness of the silicon-silicon bond remains a handicap. The diversity and flexibility, the very informational capacity required for life, would likely be far less than what carbon offers, and so the mirrored maze reveals its deeper irony. Silicon is both tantalizingly similar to carbon, and yet fundamentally constrained by its own nature. Its bonds are a little too long, a little too weak, its structures a little too rigid or too fragile. Where carbon builds the supple, dynamic machinery of life, silicon constructs towers of glass and sand. Both are beautiful, both are complex, but their complexities are of a different order. Yet the story of silicon is not one of failure, but rather of alternative triumphs. In the hands of human ingenuity, silicon has become the foundation of another kind of complexity, one not of biology, but of technology. The silicon chip, etched with microscopic circuits, now hums at the heart of our computational world. Here, silicon's crystalline order and precise, controllable conductivity make it the perfect medium for carrying information, albeit in the binary language of ones and zeros rather than the swirling, folding language of biochemistry. Even in this technological context, the chemistry of silicon is governed by its own laws. The carefully grown wafers, the dopants that control electron flow, the photolithographic masks that etch patterns at the nanoscale, all depend on the predictable crystalline order of silicon's bonding with oxygen and itself. It is not the wild, creative chemistry of carbon, but a different kind of order, precise, regular, reliable. Curiously, there are moments where the paths of carbon and silicon cross in unexpected ways. Organosilicon compounds, where silicon and carbon are joined within a single molecule, are now crafted in laboratories, offering materials with unique properties: flexible, heat-resistant, hydrophobic. Silicones, for example, are polymers with a backbone of alternating silicon and oxygen atoms, decorated with organic side chains. These materials are soft, pliable, and resistant to degradation, their hybrid nature a testament to the creative possibilities that emerge when the mirror is not a perfect divide, but a permeable boundary. The natural world, for its part, has touched upon silicon, though always at a distance. Diatoms, those microscopic architects of the oceans, build their shells from silica, their intricate patterns rivaling the finest jewelry. The spicules of sponges, too, are spun from silicon dioxide, lending strength and structure to the soft bodies of their makers. But always the silicon is locked in a mineral form, inert and unchanging, a suit of armor rather than a living machine. It is striking, then, to reflect upon the limits of our own imagination. Silicon is so abundant, so close to carbon on the periodic table, that it is a perennial favorite in the speculative fiction of other worlds. Yet as we have traced the winding paths of their chemistry, the reasons for carbon's preeminence become clear. The subtle balance of bond strength, size, geometry, and reactivity has, over billions of years, conspired to make carbon the axis upon which the wheel of life turns, at least in this corner of the cosmos. Still, the mirrored maze is not without its mysteries. There remain uncharted territories, both in the laboratory and in the universe beyond, where the boundaries between these elements might blur or new chemistries might emerge. The search for life elsewhere is, in part, a search for the unexpected, a willingness to be surprised by the forms that complexity might take under different stars, with different elements in different solvents. As we stand amidst the reflections, we might ask, what hidden patterns lie just out of sight behind the next turn in the maze? If not silicon, then what other elements might play the game of life in ways we have yet to imagine? And as we peer deeper into the mirrored hallways of chemistry, what new truths and possibilities might be revealed, shimmering just beyond our current understanding? The path twists onward, and the shadows lengthen, promising deeper enigmas as we move further from the well-lit halls of established knowledge and into the dimmer corridors where the future of life's complexity and the potential of other elements awaits its own revelation. In the hush of a laboratory before dawn, when the air is still and the glassware catches the faintest glimmer of the rising sun, the stage is set for a quiet drama that has unfolded over centuries, a drama of inquiry, of patience, and of the slow, careful dance between human curiosity and the hidden patterns of the natural world. Here, the alchemist's tools are no longer the alembics and retorts of medieval times, but gleaming arrays of spectrometers, scanning electron microscopes, and the almost magical invisible webs of computation that can model worlds within worlds. Yet the spirit of the search is unchanged, to peer into the heart of matter, to coax forth the secrets of silicon and carbon, those twin pillars upon which the fabric of possible life may rest. It is a journey that begins not with certainty, but with questions. Why carbon? Why not silicon? Can life be woven from the stony bones of silicon, as it has been from the airy threads of carbon's chemistry? The answers are hidden not only in the vast reaches of astrophysical possibility, but also in the smallest details: how atoms cling together, how molecules twist and fold, how n-pair. Ergies ebb and flow in the silent dance of electrons. To unveil these truths, scientists have devised a remarkable arsenal, each tool a bridge between the invisible and the observed. Let us drift first into the world of carbon, that old magician of the periodic table. For centuries, the study of carbon was bound up with the study of life itself. Early chemists, called at times philosophers of fire, believed that a mysterious vital force animated organic matter. It was only in the 19th century, as glassware grew more elaborate and balances became more precise, that Friedrich Wöhler, in a moment of serendipity, transformed inorganic ammonium cyanate into urea, an organic compound, dispelling the illusion that life's chemistry was fundamentally separate from that of the inanimate earth. The floodgates opened, and with them came the realization that carbon's power lay in its 4 valence electrons, its ability to bind flexibly and form vast branching chains and rings. To probe these chains, scientists have relied on a symphony of techniques. Consider the humble mass spectrometer humming quietly in a corner of the lab. Here, molecules are coaxed into the gas phase, ionized by a beam of electrons, and then flung through magnetic fields. Each fragment describes a looping arc, its path determined by the precise ratio of its mass to its charge. The pattern that emerges on the detector is a kind of signature unique to each compound, a fingerprint written in the language of atoms. In this way, chemists can deduce not only the presence of carbon, but the very architecture of the molecules it forms, the branching of a sugar, the coiling of a protein, the elegant stack of aromatic rings in a molecule of DNA. But the tools of modern alchemy reach deeper still. Nuclear magnetic resonance, or NMR, listens to the faint whispers of atomic nuclei as they align and precess in strong magnetic fields. When a sample is placed within an NMR spectrometer and subjected to a pulse of radio waves, the carbon-13 and hydrogen nuclei within respond with a series of tiny oscillations. From these patterns, scientists can reconstruct the precise arrangement of atoms in space, mapping the intricate folds of a protein, the knots and loops of a ribozyme, the subtle geometry of a drug as it fits into the cleft of an enzyme. It is a kind of atomic cartography, charting the invisible terrains upon which the dramas of life are played. If mass spectrometry and NMR reveal the shape and composition of carbon's handiwork, then X-ray crystallography unveils its hidden symmetry. Here, a purified crystal, perhaps a fragment of insulin or a piece of graphite, is bombarded with a beam of X-rays. The waves scatter and interfere, producing a delicate pattern of spots on a photographic plate or digital sensor. By laboriously decoding this pattern, scientists can reconstruct the three-dimensional lattice of atoms within, capturing the essence of molecular architecture with astonishing precision. The double helix of DNA, the sheets and helices of hemoglobin, the intricate machines of photosynthesis, all have yielded their secrets to this patient art. Yet to truly understand why carbon is so adept at the business of life, one must look beyond its structures to its habits, the way it binds, the energies with which it forms and breaks bonds, the subtle choreography of reactions that animate metabolism and replication. Here the tools become even more abstract. Quantum chemistry, a marriage of Schrödinger's equations and computational power, allows researchers to simulate the behavior of electrons as they swirl around carbon's nucleus. By modeling these interactions, scientists can predict which molecules will form, how stable they will be, and how quickly they will react. The laboratory expands to fill the memory of a supercomputer, and the experiments take place in silico as much as in glass and steel. Through this arsenal of instruments, the mass spectrometer, the NMR, the X-ray beam, and the quantum computer, carbon's story unfolds. It is a tale of flexibility and strength, of molecules that can be delicate or durable, simple or staggeringly complex. But always, in the background, there is the question: could silicon, that pale cousin lurking just below carbon in the periodic table, ever claim a similar throne? To approach this question, scientists have turned their gaze to the chemistry of silicon, a journey that requires both imagination and ingenuity. Silicon, like carbon, possesses 4 valence electrons, and in principle, it too can form 4 bonds. In practice, however, the differences begin to emerge. Silicon's larger atomic radius, its weaker hold on the electrons in its outer shell, and its affinity for oxygen all conspire to shape a different realm of molecular possibility. In the laboratory, the exploration of silicon's potential as a life-forming element has been both methodical and creative. Early chemists, working with the grey crystalline element extracted from sand and rock, found that silicon's bonds to itself are less stable than those of carbon. Unlike the robust chains and rings that carbon forms with ease, silicon tends to favour shorter, less flexible connections. Polysilanes, chains of silicon atoms, can be synthesized, but they are prone to breaking down, especially in the presence of oxygen or water. Where carbon gives rise to the endless diversity of organic chemistry, silicon's self-linking tends to result in fragility and brittleness. To probe these differences, researchers have devised experiments that test the stability and reactivity of silicon compounds under various conditions. In climate-controlled glove boxes, where oxygen and moisture are banished, chemists coax silicon atoms into bonds with hydrogen, chlorine, or other silicon atoms, carefully monitoring the resulting molecules with the same tools used for carbon: infrared spectroscopy to track vibrational modes, chromatography to separate and identify products, and high-resolution mass spectrometry to analyze the fleeting fragments. A key moment in the study of silicon's potential came with the synthesis of silanes, compounds analogous to the alkanes of carbon chemistry, but built from silicon and hydrogen. In the 19th and early 20th centuries, scientists such as Friedrich Wöhler and Edward Frankland experimented with these substances, observing their volatility and their tendency to ignite spontaneously in air. Silanes proved unstable, prone to decomposition, and reluctant to form the stable, intricate networks so characteristic of carbon's molecular menagerie. Yet the story does not end with these simple compounds. In the latter half of the 20th century, chemists began to explore the world of organosilicon compounds, molecules in which silicon is bonded not only to other silicon atoms, but to carbon itself. These experiments gave rise to a rich field of study, with applications in everything from modern electronics to the synthesis of new materials. Silicones, polymers with alternating silicon and oxygen atoms decorated with organic side chains, proved to be remarkably stable and flexible, finding their way into medical implants, lubricants, and sealants. But even here, the backbone of the molecule was not a continuous chain of silicon atoms, but rather a hybrid structure, borrowing stability from oxygen and flexibility from carbon. To test whether silicon could support the complex self-replicating molecules of life, scientists have also turned to computer simulations. Quantum mechanical models allow researchers to predict which silicon-based molecules might be stable, which might form the basis for information storage, energy transfer, or catalysis. These virtual experiments often confirm what is seen in the lab, that silicon's bonds are less versatile, its molecules less adaptable, its structures less conducive to the subtlety required for life's chemistry. Silicon, it seems, is a builder of rocks and crystals, not of the soft, mutable tapestries that living cells require. Nonetheless, the spirit of experiment persists. In the 21st century, a new wave of synthetic biologists and chemists have taken up the challenge afresh, wielding the tools of directed evolution and molecular design. In carefully controlled environments, researchers introduce silicon atoms into the active sites of enzymes, coaxing proteins to catalyze the formation of silicon-carbon bonds, a feat never before achieved by living organisms. In a landmark experiment in 2016, Frances Arnold and her colleagues engineered an enzyme capable of forging these new bonds, demonstrating that with the right nudges, biology can be taught to manipulate silicon in ways once thought impossible. These experiments are carried out under the bright light of fluorescence microscopes, their results analyzed with the sensitivity of chromatographs and the precision of next-generation sequencing. Each step is a testament to the ingenuity of modern science, the ability to redesign life's machinery, to push the boundaries of the possible, to create, in miniature, the conditions under which alternative chemistries might flourish. Yet, even as the frontiers of the laboratory expand, the fundamental limitations persist. Silicon's tendency to react avidly with oxygen, forming the unyielding lattice of quartz, remains a barrier. In the oxygen-rich atmosphere of Earth, silicon-based molecules are rapidly oxidized, their delicate architectures collapsing into dust and stone. The dream of silicon life, it seems, would require not only new chemistry, but a new world, a planet where water is rare, oxygen scarce, and the slow dance of atoms can proceed along unfamiliar paths. Through all these investigations, the tools themselves become characters in the unfolding story. The spectrometer, with its ability to see the unseen, the microscope, that unblinking eye, the computer weaving webs of possibility across the digital ether. Each instrument, each technique, is an extension of human perception, a means by which the boundaries of knowledge are gently, persistently pressed outward. And so, in laboratories scattered across the globe, under the steady hands of chemists and the curious gaze of physicists, the question of silicon and carbon remains alive, a riddle posed not only to our instruments, but to our imaginations. The alchemists of old sought to transmute lead into gold. Their modern descendants seek to transmute the raw stuff of the universe into meaning, into understanding. In the flicker of a monitor, in the hum of a magnet, in the patient click of a pipette, the secrets of possible life are coaxed, molecule by molecule, from the silence of matter. The journey is far from over. For as scientists press deeper, new tools emerge, synchrotrons that fire beams of X-rays with the brilliance of 1,000 suns, cryo-electron microscopes that freeze molecules in mid-motion, and algorithms that can predict the folding of proteins or the dynamics of new hypothetical molecules. Each innovation opens a new window onto the chemistry of life and its alternatives, each experiment a step further down the labyrinthine corridors of possibility. But the laboratory is not the only theatre where these questions are pursued. Beyond the glass and steel, beyond the ordered chaos of benches and fume hoods, a new frontier beckons, a frontier that stretches out into the stars, where the chemistry of carbon and silicon may play out on scales far grander than any test tube can contain. There, in the cold vastness, the tools of observation become telescopes and spectrographs, tuned to the faint glimmer of distant worlds, searching for the spectral fingerprints of life, or something like it, written in the light scattered across the cosmos. And so, as night settles over the laboratory and the last notes of the day's experiments fade into darkness, the story waits to be continued. The tools are cleaned and set aside, the data archived for future thought. Outside, the stars wheel overhead, silent witnesses to the enduring quest, a quest that will carry us inexorably from the measured rituals of the lab to the boundless dreams of other worlds and the tantalizing possibility of life as yet unimagined. All through human history, we have sought the threads that tie us to the fabric of the universe. In quiet moments, under starlit skies, philosophers and scientists alike have pondered what it truly means to be alive, to belong, to arise from matter and yet be more than mere dust. The contemplation of silicon-based life, so different and yet so akin to our own carbon origins, opens a rare window, one that lets us peer not just outward to the possibilities of distant worlds, but inward toward the very heart of what it means to be living, thinking, and aware. Silicon and carbon, two elements, neighbors upon the periodic table, each with 4 valence electrons perched at the edge of their atomic shells, poised for connection. They are cosmic siblings, forged in ancient stars and scattered across the galaxy. Yet from this simple kinship, a universe of difference unfurls. Carbon, the backbone of earthly life, spins its flexible chains and rings, building the endless variety of organic molecules that compose our cells. Silicon, steadfast and sturdy, forms lattices and minerals, the bones of planets and the brains of our machines. The contrast is striking, yet never absolute, for the division between them is not a wall, but a bridge, one that invites us to contemplate the wider possibilities of existence. As we let our minds drift into the possibility of silicon-based life, something subtle but profound begins to shift in our sense of self. For so long we have taken for granted the notion that life, as we know it, is not just a quirk of chemistry but the only way that matter can awaken. The presence of silicon, so abundant across the cosmos, yet so reluctant to mimic carbon's organic dance, challenges this assumption. Its potential for forming its own kinds of molecules, perhaps in the depths of alien worlds or in the searing heat of gas giants, suggests that life is not a singular melody but a symphony, one whose harmonies may be played upon very different instruments. It is humbling and quietly exhilarating to imagine that somewhere out there, in the dust and vapor of distant worlds, silicon may be weaving the patterns of life in forms utterly strange to us. Perhaps in the thick orange mists of a Titan-like moon, or in the mineral labyrinths beneath some ancient Martian crust, there could arise creatures whose bodies are not built from carbon's supple chains, but from the solid crystalline frameworks of silicates. Their cells, if indeed they have cells, might be less like the soft, fluid bubbles of our cytoplasm, and more like tiny, intricate cathedrals sculpted from glass and stone. And yet, what is life, if not the capacity to organize, to replicate, to pass on information, to adapt and endure? Whether by the grace of carbon's flexibility or silicon's resilience, the essential mystery remains. How does mere matter awaken to itself? How does a molecule, blind and mute, become the vessel for thought, for longing, for the slow flowering of consciousness? These questions, as old as your species, find new resonance when we reflect upon our elemental origins. Every atom of carbon in your body was born in the heart of a long-dead star. Every silicon chip that powers our cities and our computers once drifted as stardust in the void. We are, in the deepest sense, children of cosmic fire and time. To imagine silicon-based life is not just to speculate about the alien. It is to recognize that our own existence is just one chord played by the universe upon the strings of chemistry. The philosophical implications of this are manifold and profound. The possibility of life founded upon silicon or upon any other element invites us to reconsider the boundaries of life itself. Is life defined by its chemistry or by its patterns, by the flow of information, by the persistence of organization, by the capacity to evolve? If, on a faraway world, we were to find a network of silicon-based structures replicating, adapting, and passing on information, would we recognize it as kin? Would we see a flicker of ourselves in its unfamiliar mirror? For centuries we have gazed at the stars and wondered whether we are alone. The search for extraterrestrial life, whether carbon-based, silicon-based, or otherwise, is as much an inward quest as it is an outward one. It is a search for connection, for a sense that our own being is not an accident, but part of a vaster order. The notion of silicon-based life widens the circle of possibility, reminding us that life may be far more ubiquitous and far more diverse than we have ever dared to imagine. Consider for a moment the impact this realization could have on our sense of meaning. If life can arise wherever conditions allow the right dance of atoms, whether they be carbon, silicon, or something stranger still, then the universe is not a silent, indifferent expanse, but a fertile ground for the flowering of being. The emergence of life, in all its myriad forms, becomes not a miracle confined to a single blue planet, but a natural unfolding of the cosmos's potential. We are not the sole focus of creation, but one note in an infinite song, yet there is more. The contemplation of silicon-based life also invites us to reflect on the unity of matter and spirit, of the physical and the mental. Our very thoughts, as you drift now in this gentle darkness, are the product of carbon molecules arranged in intricate, ever-shifting patterns. The possibility of silicon-based life reminds us that consciousness itself, for all its mystery, is rooted in the material world. It is not the exclusive domain of carbon, but a property that matter may acquire in many guises under many suns. This realization is both unsettling and beautiful. It suggests that our sense of self, our cherished subjectivity, is not a unique quirk of carbon's chemistry, but a possibility that the universe holds in many forms. It invites us to humility, to recognize that our way of being is not the only way, and that the cosmos may hold other minds, other awarenesses born of different elements, dreaming their own dreams beneath alien skies. The dialogue between silicon and carbon is not merely a matter of chemistry or biology. It is also a conversation between the artificial and the natural, the created and the evolved. For as we probe the mysteries of silicon, we find ourselves not just seeking life elsewhere, but also forging new forms of life here. Our computers, our networks, the artificial intelligences we have begun to weave from silicon circuits, these too are products of the universe's elemental creativity. They are, in a quiet sense, our own attempt to coax awareness from the bones of stone. This raises questions that are as philosophical as they are scientific. If carbon-based life can give rise to silicon-based minds, what does this say about the nature of consciousness? Is it a property of matter, waiting to be awakened wherever complexity arises? Or is it something rarer, something that requires the particular touch of carbon chains, the gentle warmth of organic chemistry? Are the silicon minds we build truly aware, or do they merely mimic the outward forms of thought? These are questions without easy answers, and perhaps they will remain open for as long as we ponder the nature of life. But in the asking, we are drawn ever deeper into the mystery of our own existence. The possibility of silicon-based life, whether natural or artificial, invites us to see the universe as a place of possibility, of becoming, of ceaseless transformation. It reminds us that the boundaries we draw between life and non-life, between organic and inorganic, between self and other, are not fixed, but fluid, shaped by the play of atoms and the unfolding of time. In the gentle hush of the night, as your thoughts begin to drift and unravel, let your mind wander along these elemental pathways. Imagine the ancient stars, laboring for eons to forge carbon and silicon from the simple hydrogen of the early universe. Picture the restless clouds of dust and gas, swirling, colliding, giving birth to worlds of every shape and kind. Imagine, on some distant shore, the slow, patient work of chemistry as elements find their partners and begin the long ascent toward life. Perhaps, in the mineral depths of an alien planet, silicon atoms are reaching out, linking together in ways we have yet to imagine. Perhaps in the frozen stillness of a distant moon, a new kind of awareness is stirring, built not from the molecules of our own bodies, but from the elemental bones of stone and sand. And perhaps, as we reach out into the cosmos with our machines and our minds, we are beginning to participate in this grand unfolding, adding our own verse to the universe's endless song. The contemplation of silicon and carbon, of their differences and their kinship, is not just an exercise in chemistry or astrobiology. It is at its heart a meditation on connection, on the hidden threads that bind all things together. For in the end, whether life arises from carbon's supple chains or silicon's crystalline frameworks, it is the impulse to connect, to organize, to awaken that defines the living. It is the spark that leaps from star to planet, from atom to mind, from the quiet dust of space to the soft dreaming thoughts that cradle you now. As you lie here, suspended between wakefulness and sleep, you can feel the gentle pull of these questions, like a tide drawing you outward into the vastness. You and I, and every living thing, are woven from the same elemental cloth, shaped by the same cosmic forces, animated by the same restless urge to be. The possibility of silicon-based life does not diminish our uniqueness, but enriches it, placing us within a tapestry that is richer, stranger, and more beautiful than we have ever known. So let your mind drift on these currents, feeling the deep kinship between yourself and the universe that made you. The dance of elements, the play of possibility, the silent promise of life in all its forms, these are the music of the cosmos, the lullaby that carries us through the darkness and into the dawn. Somewhere, perhaps, new forms of life are stirring, new patterns are emerging, new minds are awakening to the wonder of being. And in this endless unfolding, we find not just our origins, but our destiny, to witness, to wonder, and to dream. As our journey through the shimmering possibilities of silicon and carbon gently drifts to a close, we watch their cosmic dance fade, like a comet tail fading into the hush of space. Let your mind float softly on these starry wonders, and when you're ready, return with me for more Dreamtime tales that whisper the secrets of the universe.